All right, howdy, Tucson, Arizona. We are going to take this polynomial, f of x is equal to x plus 2 times x minus 3 times x plus 6, and we're going to determine the degree of the polynomial. We are going to also identify the leading coefficient. That's going to help us identify the behavior of the function as x approaches negative and positive infinity. And strategy, and we have to also locate zeros and then determine the multiplicity of 0 at 3. And so the strategy that we're going to use is to take this factored polynomial and we're going to just multiply the factors. So we have 3 binomials, and so of course from algebra 1 we know that we can multiply binomial times binomial by either FOIL or distributive property, same thing, right? And so x times x is x squared. Outside terms, negative 3 times x is negative 3x. Inside terms, 2 times x, 2x. And then our last terms, the product of 2 and negative 3 is negative 6. And so we're going to do that, and it's going to give us a trinomial. And then we're going to multiply that trinomial times the last factor or binomial given this function, okay? So again, x times x is x squared, x times negative 3x, plus 2x, and then we're going to multiply 2 and negative 3, negative 6. So we're going to combine our like terms, and we're going to end up with x squared minus 3x. Just kidding, ha ha ha. Minus 1x, or just minus x, right? Minus 6, and so 2x plus x plus 2 times x minus 3 is x squared minus x minus 6. I'm going to take that and multiply it times the last binomial here, or factor, same thing. And we're going to distribute. So I'm going to distribute x times x squared is x cubed. X times negative x is negative x squared. X times negative 6 is negative 6x. 6 times x squared, 6 times negative x, and 6 times 6. And that is going to give us this polynomial in standard form. And so x times x squared, x cubed, x times negative x squared, x times negative 6, negative 6x. 6 times x squared is positive 6x squared. 6 times negative x is negative 6x. 6 times negative 6, product of 6 and negative 6, okay? And so that looks really messy, but of course we can combine our like terms. And so x squared term here, x squared term here, we're going to combine those, and we have 2 x terms that we can combine. And so this function condenses to x cubed, so f of x is going to be equal to x cubed, negative x squared plus positive 6x squared gives us 5, positive 5 x squared, negative 6x plus negative 6x gives us a negative 12x, and minus 36. Okay, and so yeah, that's that polynomial in standard form, descending order. And so very clearly, our degree, our leading term here is x to the third power. And so the degree of this function is the leading term, the highest exponent, which is 3. So our degree is 3. Our degree is 3. Yeah. Something else, some very important information I think that you're going to need for the next strategy in this activity is to, in graphing, is to, let's just go and identify our y-intercept. And you'll see in a few minutes why that's going to be important. So our degree is 3. Our leading coefficient, so to abbreviate that, our leading coefficient is positive, right? Because our leading term here is x cubed. 1 times x cubed is just x cubed. So a positive 1 times x cubed is x cubed. And so our leading coefficient is positive. That's important. The next strategy is to, again, graph this thing, but we're going to take care of something else that's really important in terms of graphing this. We're going to identify the y-intercept. So f of 0 tells us just basically when x is 0, right? And it's our constant. And so if this were 0, this would go away. If x were 0 here, this would go away. If x was 0 here, this would go away. And so what's left is that constant. So f of 0 is negative 36. And you'll see in just a few minutes why that's important. Okay, so our y, and that's our y-intercept. That is our y-intercept. Okay, so that's important information. And so in order to determine, or one strategy to determine as x is approaching positive and negative infinity is to graph this sucker. So that's one way to do it. We could also do it algebraically, but I think it's kind of fun to graph it. So we're going to graph this polynomial, and by locating the zeros, which is one of the activities that you're expected to be able to do as well. So the zeros. So how do we find? So it's very crucial that we understand how to identify the zeros, because that's imperative to graphing. So over here are zeros, and so given the original problem, x plus 2 times x minus 3 times x plus 6, we're given these 3 factors, and in order to identify the zeros, we're going to set each factor equal to 0. Set each factor equal to 0, and that will give us the information that we need. Okay, and so what does that mean? What does that look like? Well, that looks like this: x plus 2 equals 0 is going to give us, I'm going to subtract 2 from both sides in order to isolate x. So x is equal to negative 2. And x minus 3 equals 0. I'm going to add 3 to both sides. And x plus 6 equals 0. X is going to equal negative 6. And so those are our 3 zeros in this cubic function. So this and this, these zeros become important when it comes to graphing. Okay, so back to this section. And we're going to graph this polynomial, keeping in mind the work we just did to identify the zeros. That's really crucial. Okay, so you have graph paper? Super, I do not. And so I know that x is negative 2. X is also negative 6. So negative 2, 3, 4, 5, 6. Negative 6 is here. And x is also positive 3. Okay. And so my 3 zeros are really, really important, because that tells us where this function is intersecting along the x-axis, intersecting this coordinate plane along the x-axis. Okay, so we've got our zeros identified. It's important to kind of determine which, we know that it's cubic, So I know that it's cubic. So I know that this thing is either going to do something like this, or it's going to do something like this. I just don't know which. And so we can quickly determine which way this cubic function is moving. Okay, and we can do that by thinking about what we did here. We found that y-intercept. Okay, so our y-intercept is going to cross the y-axis at negative 36. Well, if you look at your coordinate plane, negative 36 has to be someplace here. That could be a negative 36, okay? Has to be someplace, on the y-axis between the third and fourth quadrant, right? Crossing the x-axis, the y-axis, okay? And so our next step, so I know that what's happening between -2 and -3 is something like this. That function is doing something like this. And so that means I can go like this. And between -6 and -2, it's going to be above the x-axis, something like that. Okay. And so I have just given a generic graph or image of this function. Okay. And so zeros are really important to identify first. If your intention is to graph, to look at the behavior graphically is to also study what's happening. Okay. And so if we can look at the end behavior. So as x approaches positive and negative infinity, we can look at what is happening. Looking at this function graphically, we can determine what is happening. This function is going from the behavior is going from here, this function is going in this manner, right? That's that end from positive infinity. Okay. Okay, so to the left, it's negative infinity. This function, so we have negative infinity here. So this function from here is going here and going in this area, this manner. So we go from here, from here. And so we can look at from negative infinity what's happening. So from negative infinity, this function is going down infinitely. So from negative infinity, we see that it's going down infinitely. From positive infinity, it's increasing infinitely. So that's one way to look at, graphically, that's one way to look at the behavior of the function. Another way to look at it, which is a preferred method, I think for me, is to study the leading coefficient. And so we were expected to find that leading coefficient, that leading term, okay, which is x3. So if we study the leading coefficient, if we study the term of the leading coefficient, so the leading term, I think is better, given is x cubed. Okay, and so if we, I guess you need to be able to see that. If we study the leading term of this polynomial, it's x cubed. So, I mean, if you imagine if this were negative, any negative number, what's going to happen? So if I replaced this, if this were negative, how many x's would I have? 3, right? So if that x were negative, I would end up with what? A positive or a negative? I would end up with a negative, right? And so the behavior of this function as it approaches negative infinity, we can see that graphically. I just showed you that graphically. Graphically, we can see that it's decreasing infinitely, so that's negative infinity. Algebraically, we can see that that is also the case, okay? So what if it were positive? So graphically, we can see that it's increasing, but algebraically, we can also show the exact same thing. That if it were positive, I'm just going to change these all to pluses. If they were all positive, a positive times a positive times a positive is what? It's also a positive. And so as this function is approaching, and we can see that graphically, as it's approaching positive infinity, the behavior or the end function is also towards positive infinity. Okay. All right. Multiplicity at 3. So multiplicity at 3 refers to multiplicity of 0 at 3. It basically, let's see, multiplicity of 0 at 3. It basically refers to, if you look at how many factors, we have 3 factors, that's true. X plus 2 is a factor, x minus 3 is a factor, x plus 6 is a factor, and they are all distinct. We have this function intersecting the x-axis on the coordinate plane in 3 distinct places. And so the multiplicity of 0 at 3 is 3. Okay. So bring those questions and talk soon.